So before we move on here, we're going to want to label our axes a little bit better because it will be easier to do that way. So along this axis, we know that we have miles, so we'll go ahead and type that in and change that to miles. And here we'll have the number of days. Now this is where things get a little bit more interesting. You see that there's a third dimension here. That third dimension is keeping track of the number of days. Now if we're only looking at one day, we really have a two-dimensional graph. It's usually the usual thing that we'd see, cost against the number of miles. What we're about to do is we're gonna, actually let's change this and call this cost versus miles and days. And what we're gonna do now is we're going to click on the graph, and instead of having just the 1 day situation, we're gonna go ahead and drag that data set down to encompass all the 10 days that we have. And you'll see right away that we have all 10 of those number of days situations looked at for the cost. So if we hold the number of days fixed at 1 day, then this is our cost function right here. If we hold the number of days fixed at 2, then this is the cost function for that. And you can click on these individual lines and it will show you that these are the costs associated with the points along this line, having the truck for 2 days at a variable number of miles. And similarly, we can do the same thing. Click on the third one, having it for 3 days, 4 days, 5 days. And now you can see that not only do those lines get higher in a two-dimensional graph, but actually in a third-dimensional plane, if you were walking up this thing, it's as if you were walking up a bunch of steps and going actually higher into the third dimension, which would be the vertical upwards dimension. So one cool thing I can do here is I can right-click this graph and do a 3D rotation. And under the X rotation, I can start to move this thing around, and I can actually see the geometry of this, that these actually look like individual steps along a staircase. And each of these lines is perfectly linear, but they're located with, it's as if you kind of took 10 different people, they're holding 10 different rulers, but each at a different height, yet all of those rulers are parallel to each other. And now that we see we have cost against miles, and this axis represents the number of days. Well, in theory, mathematically, we could have infinitely many day values in between 1 and 10, right? I could have actually typed in 1.5 for days right here, and it would have shown me a line. Now, for this example, we know that you can keep the number of keep the truck for a fixed number of days, that being an integer, positive integer value, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But in theory, mathematically, this variable could be continuous, not discrete like it is here. It could have 1.1, 1.2, etc. So actually, one of the things we do, like with a scatter plot, is we try to interconnect, right? If these were all points, then we could try to interconnect the points. And the way we would do that is by inserting a different type of graph. So one thing I can do here is change the chart type. I'm going to rotate back a few degrees, back to about 20 degrees. So I'm looking at the original graph. And I'm going to change this chart type, right-click, and select Change Chart Type. And we are going to select a surface. Now a surface, what it will do is it will try to interjoin all the pieces of the graph. And you can see that it's done that. It's now treating days as continuous, meaning that if I wanted to pick 1.1 days, that would be somewhere along what we call a plane. And this is called a plane. The analogy to a line in 3 dimensions is called a plane. It's like a flat sheet of paper, if you will, that somebody's holding up at an angle. And these different colors here are actually, this is actually called a contour coloring, and they kind of show us the different elevations. So the dark blue is the highest elevation, the orange is the lowest elevation. If you were walking up this thing, then each segment represents kind of a different elevation range. So now we have a 3-dimensional graph. And this is our first kind of way of thinking about this 3-dimensional graph, which is a series of infinitely many days between 1 and 10 being looked at against really the variables that we care about are cost versus miles for variable number of days. So the next question we could ask is, what if we decided to change the way we do the reduction function? So what does the cost function look like if d equals 1? We did that. What if d equals 2? We did that. We just looked at the situation where we incorporated the surface graph. And now let's change our scope of thinking. So what does the cost function look like if m equals 100? So in other words, what is the reduction function, ignoring all the things that we've done just now, and we wanted to take a look at the cost function if m equals 100. Well, so what we're going to do is we're going to treat d as the variable now. So d is our unknown, and m is fixed to be 100. So maybe you know you're driving 100 miles, but you don't know how long you're going to need the truck for. So your cost function is going to be $19.99 times the number of days, which is the variable, plus the 47 cents a mile you pay times the number of miles that you drive. Okay, well, we can reduce this to 19.99d plus what's going to end up being 4.7. So your overhead in this case is $4.70. And again, notice that this is a perfectly neat linear function where the slope is now going to be 19.99. So we have just fixed m to be 100, and now we want to take a look at a graph of that. So let's do the same thing, or a very similar process. We are going to go ahead and delete some of our data here. So I'm going to take away this graph. Actually, what I'm going to do is I'm going to copy it, and I'm going to paste it into our Excel document here, or sorry, our PowerPoint document here. So I'm going to go ahead and paste that, just so I have a reference of what that graph looked like. And now I'm going to come over here and I'm going to delete this guy, and I'm going to change my data. So this column, what it will now keep track of is the, I'm going to remove all of these mileage markers. I'm going to take that away, and I'm just going to look at the cost, treating the number of days as being variable for 100 miles. Okay, so you notice that driving 100 miles is going to cost you. That's 47 cents per mile. For 100 miles, it's going to be, sorry, not 4.7, but $47 to drive 100 miles. But the increase in cost here is due to the fact that I keep the truck for an extra day. Okay, so let's take a look at that data. So we're going to insert a scatter plot, and we're going to use the scatter with smooth lines. I'm going to select my data, and I'm going to now add a series name, which is going to be the cost for m equals 100 miles. And my x values are going to be the number of days here. And then my y values are going to be the resulting costs for those different number of days. So there it is. And I'm going to click OK. Click OK again. And what I'm going to do here is just insert my label so I know what I'm looking at. So my y-axis is going to keep track of my cost, and my x-axis keeps track of the number of days that I keep the truck for. So you again notice that, well, we don't have a vertical intercept here because in theory, you can't rent the truck for 0 days. If you do that, you can't drive 100 miles and expect not to pay for the day. So it doesn't make much sense to look at a vertical intercept here. But again, the function is linear, as we observed, $19.99 for each additional day. And we're driving a total of 100 miles. So again, our question becomes, well, can we look at this thing for a variable number of miles? So what if m is equal to 200? Well, if m is equal to 200, I can now incorporate another function here and call this 200 miles. And now I'm going to copy this column here and drag it over. So now I have the total cost for renting for 1 day under the assumption that I drive 200 miles, all the way down to if I keep the truck for 10 days and still drive 200 miles. And I can let my graph incorporate this effect as well. And again, we notice that the functions are perfectly linear because the cost for additional day is $19.99. The only difference is, now you're paying a little bit more relative because the number of miles driven is double that of what it was previously. So the cost is going to be roughly double that, not quite double that because we have the effect of the day going in there. And I can do the same thing for 300. So equals this one plus 100. And I can drag this out for a few different miles, maybe up to, 600 miles if I'm traveling across the state. And now I can select my graph to incorporate that as well. Oops, missed one row there. And so these lines in sequence go from basically driving 100 miles, 200 miles, 300 miles, 400 miles, 500 miles, and 600 miles, under the assumption that I keep it for a variable number of days. I can do the same thing I did previously. I'm going to remove the graph completely, and now I'm going to insert the special type of graph, which is 3D lines. I'm going to select my data, and I'm going to add a, let's see, the series. The variable that I want to keep track of is the number of days right there. And the series name is going to be days. Oh, excuse me, nope, I didn't want to do that. This is actually going to be the number of miles that I drive. So this is the cost function for driving 1 up to 10 days for 100 miles. And this is going to be my corresponding, the vertical axis is going to represent my corresponding cost. So, oops, I need to move this over actually. And so now I can see, what the cost is for 100 miles driven, holding the number of miles fixed at that value. So I'm going to add again axis titles so I can see what I'm looking at. This is my cost. This is the number of days that I keep the truck for. And this 100 over here right now just represents the single case of driving 100 miles. Okay, well, now I can actually incorporate the other situations as well. So I want to look at what's the cost for holding the number of miles fixed at 200 or 300, or maybe all of the number of mileages between 100 and 600. And again, I get these linear functions that are a little bit different because now I'm looking at the cost versus days instead of cost versus miles, but I'm looking at it for a fixed number of miles. And again, I can do the exact same thing, change this chart type to now fill in the gaps because I could technically drive, and in reality, 152.7 miles. So if I change my chart type to a surface, I'm going to notice that I have pretty much the same looking graph. Now, what's the relationship between this graph and this graph over here, which, wow, I don't know what happened. I think it's still linked to the same spreadsheet. Well, they're exactly the same, except when I rotate this, do a 3D rotation here, what I'm looking at now is the cost versus the miles, where this axis right here keeps track of the number of days. So it's the exact same function, it just depends on what two variables I'm looking at. So in 3 dimensions, cost, days, and miles produces the same graph, it just depends on what two variables I'm looking at the same time. So we'll leave that there. The main takeaway right now at this point is that we get what is called a 3-dimensional surface. Surface is really just what we use to talk about graphs in 3D. Instead of calling them lines or curves, that doesn't really make sense in 3D. This is the analogy of a line in 3 dimensions, and it's what's called a plane. So if you're dealing with a linear, where both functions are linear, in terms of the reduction function with respect to one variable or the other, if they're both linear, then the resulting 3D graph is a plane. And in the next video, we'll go ahead and take a look at the more interesting function where things do not behave quite as linearly, or at least not in both dimensions, the x and the y dimension. And we'll look at the compound interest model, but we'll go ahead and stop here. So play around with this Excel spreadsheet a little bit to try to make sense of what's going on, and we'll now proceed into one where the reduction function, at least one of them, is not linear.